I did want to welcome everybody to tonight's MakerFX Make the Sun Work for You class. It is now 6 o'clock. We're expecting about 24 people who RSVP'd to this class tonight. We're far from that number now, but that's okay. Harry is with us, and he is going to be doing the presentation tonight, so I'll be turning it over to him. Harry's a longtime member at MakerFX. He's also done some incredible things at MakerFX with resin, with 3D printing, with woodworking, with the Maslow in the back by the CNC. He's done a lot of stuff at the shop. He does have his own solar panel array in his backyard. The picture you saw for the invitation in the class for tonight, that's actually from his backyard. So those solar panel arrays back there are his. So he's a man of many talents, and he is going to be imparting some awesome knowledge with us tonight. I know I've been trying to get to this class for months and always had a schedule conflict. So really excited to be able to get to this tonight. We are going to be recording this class tonight, but I will not be recording the videos, just the presentation. If you have a question, please use the feature within Zoom to raise your hand. That will allow the presenter know that you have a question. You can also type it out in the chat box, but if it's too long or too detailed, just use the Alt-Y or Option-Y, depending on your computer system, to raise your hand, and we'll know that. And we will get all your questions answered, and probably a lot of your answers questioned tonight. So without further ado, I'm going to turn it over to Mr. Armstrong, and he is going to present to us tonight on how to make the sun work for us.
So again, my name's Harry Armstrong. The goals for the class is we're going to learn the different types of solar energy. We're going to just touch on some hobby uses for solar energy, some other everyday uses that you can use solar energy for, and the majority of the time is going to be spent on the residential electric planning, design, and installation. So let's just jump right in. So a lot of people, when they think about solar energy, the first thing that comes to mind is generating electricity. However, you can also use the thermal power of the sun to heat things. And some of the things that I'll go over in my presentation here is heating your normal hot water, your potable water in your house, like it's in your hot water tank. Actually heating your house with heat from the sun warming air to heat your house. And then I've made 3 different solar ovens for cooking food. As far as the electricity goes, like I said, we're going to touch on hobby level sensors, some of the toy uses that are out there, but the majority of the time of the class is going to be spent on regular household energy generation. So when we talk about warming the water or heating the water of your house, like in your hot water heater, there's 2 different ways of doing it. Here in Florida, we're lucky because it rarely freezes. So the most efficient way of warming water or heating water here in Florida, if you want to do it thermally or with solar, is what's called the direct method. Basically, the water is pumped from your hot water tank up onto the roof or into panels somewhere that's facing the sun. The sun warms the water, and then it goes back into the tank. And it just cycles all day long and gets your water hotter and hotter. Again, it's good for areas like ours that rarely freeze, because you can imagine if you try to install one of these, like up in New York in the middle of winter, you're trying to pump water up onto the roof. If it sits there for more than 2 seconds, it's going to be frozen solid. It is more efficient than indirect systems, which we'll talk about indirect systems here in a minute. But the reason it's more efficient because you're heating the water that's actually going right back into the tank, the water that you're using. This is the way the solar pool heaters work. You see them on people's roofs, a big like black rubber bladders that are up there. It basically just pumps water up through those. Those get hot and warm the water, and then it goes back into the pool. So this is a pretty simple diagram of a direct system. It's pretty simple. The water comes out of your hot water heater, out the bottom, that's where the cold water is in your tank. The hot water would be at the top. Just because hot water rises. So it pumps the water up into the bottom of the solar collectors on the roof, and then it comes out hotter than it went in, and it basically just cycles that all day long. These solar collectors on the roof, they're basically just copper pipes, typically with copper flashing bonded to the copper pipe somehow, so that the sun shines through a glass. It does the greenhouse effect. In addition to that, the sun heats up the flashing, which heats up the pipe, which heats up the water. So it's a pretty simple setup. This particular storage tank is drawn as a solar hot water heater tank, and there's a couple differences between a solar hot water heater tank and a normal hot water heater tank. On a normal hot water heater tank, you've got a heating element in it, and there's one cold input, and then there's one hot output that goes to the house. On a solar tank that's designed for solar, there's two inputs and two outputs. So you've got the normal cold coming in and the hot going out to the house. We also have another set of cold coming out to go to the solar panel and the hot coming back. There are companies out there that make some ingenious ways to get around this if you want to use your normal hot water heater tank in your house and turn it into solar. Typically, they involve taking out the drain plug that's at the bottom, and then they make this kind of unique thing that you slide in there with two copper pipes in it, and that acts as your in and out for your solar. So you can actually convert your regular normal hot water heater tank to a solar tank if you wanted to. So the other method is what's called indirect, and the indirect method basically takes a liquid that's freeze-proof. Most of the time they use glycol, which is a type of alcohol, and they pump that up through the panels on the roof instead of the water, like the regular water that's in your hot water heater tank. And the glycol gets heated, and then it runs through a heat exchanger inside the hot water tank. It is less efficient than a direct system. However, since the glycol can't freeze and the glycol is the only thing that's outside, you don't have to worry about things freezing. They are a little bit more complex. This is a diagram, probably a little more complex than it really is, but basically, there's a heat exchanger inside your hot water heater. So obviously this has to be a special hot water heater. And this heat exchanger is just basically a coil of copper pipe. That's about all it is. So the glycol is in these tubes here and in all this, but it's a closed system, so the glycol can't get out. So what happens is it goes through a check valve, a pump pumps it up to the collectors, just like the other one did through regular water. And then it comes back down and then through the pipe. So these pipes get hot, and then the pipes heat the water that's in your hot water heater. So you can kind of imagine that it's not quite as efficient as actually heating the water itself. A couple of challenges or complexities with this system is, since it's a completely self-contained system, if it's in the middle of summer and this thing's getting really hot, the glycol in here is going to expand. And so you have to provide some type of expansion for it. So that's what this expansion tank is for. It's kind of like if you ever done any work on a well to provide water pressure. So as the glycol expands, it pushes down on a bladder inside this expansion tank and compresses the air that's in here. That way it doesn't start blowing things out just because of the pressure that's in it. So to give you an example of a direct thermal solar hot water system, I've got some pictures of mine on here. Virtually all of my hot water is heated by the sun. I still have one child at home, so between my wife and I and my child, if we all take showers after each other, sometimes we can run out of hot water, so the electricity takes over from there, the regular heating element in the hot water heater. I have 4 thermal panels on the roof and then 1 small electric solar panel on the roof. The electric solar panel is just a little 12-volt panel that powers the pump that pumps the water up through the system to the roof. And it's very simple. Basically, if the sun's out and the sun's out enough to heat the hot water, there's going to be enough sun to generate 12 volts to turn the pump on to pump the water up through to heat the hot water. So it's a really simple system. I do have 2 hot water storage tanks that are connected together, just kind of because I bought one of them and somebody else gave me another one. So I connected them in series. So I basically have 115 gallons of hot water. So it does last quite a while. So on the roof, these three long things, and this bigger square one up here are the thermal ones. That's the ones that the sun shines through. You really can't see through it too well, but there is copper pipe that goes back and forth with the copper flashing on it to heat the water up. You always want to run the input to these things in the bottom. That way it helps flush out any air that's in there if there's when you first put the thing together. And right there is the 12-volt electric solar panel that drives the pump. Now, way back when I was investigating all of this, I found a company in California called solarroofs.com. And the story about the company is the guy spent much of his life installing thermal solar systems, these thermal hot water heaters. And the ones that were out there on the market for most of the time were ones that looked a lot like this top one. They were 4 foot by 8 foot with an aluminum frame, a glass front, and they weighed quite a bit. In fact, the way the guy describes it is, if you wanted to put it on your roof and obey all the OSHA regulations, a crane had to put it on because it was heavy enough where people weren't allowed technically to put it on your roof. So his thinking was, well, there's got to be a better idea than this. So what he did is he designed this type system down here, the long and narrow ones. So what these are is, instead of using this really thick extruded aluminum, he uses kind of thinner aluminum for the frame. And instead of using glass, he uses Lexan, which is much, much lighter. And then he made the things 12 feet long. So what you can do with these is you get them, you lean them up against the side of your house, and they're taller than, if it's just a single story house, they're taller than the roof. So you climb up on the roof, and you're literally, one person can pull it up and put it in place. And these three are just ganged together, and you just get as many of them as you want, depending on how much capacity you need. So I bought this system from him, including the pump and the solar panel and all the fittings and everything. And then probably a year or two later, I was at USAVE Building Materials in Orlando, down on, I think it's on OBT, kind of near downtown. And I was walking through the back there, and they had one of these large solar panels, brand new in the box. And I think they wanted like $100 for it or something. So I bought it. So I figured I would just add it to my system. I got it home, and the only challenge I had with it was kind of funny thinking about it now. The thing, I don't know where it came from, but it's all metric. So the fittings on it were not 1/2-inch copper. They were 12 millimeter. So I had to find a fitting to adapt compression 12 millimeter to compression 1/2-inch copper, which Granger did have one. They're solid stainless steel, and I think they're like $50 a piece, but they're the only place I could find for one. So I had to buy 2 of them, obviously, one for the top, one for the bottom. But anyways, so that's the way this system works. Inside, these are my 2 hot water tanks. And this plumbing looks a lot more complicated than it really is. But basically, this is the one I would consider the hotter tank, and this is the cooler tank. So the top of this tank is plumbed directly into the house. That would be this, if you can see my mouse, that would be this copper pipe that comes up and goes into the house. Now there's a little silver thing right here. It's kind of hard to see in the picture, but there's a little silver thing here that's called the tempering valve. And what that does is that's like a thermostat for the water. So what it does is it mixes, this is cold water coming into it. So you don't get like 150 degree, 180 degree water going into your house. This tempers the water down to a decent temperature before it goes in the house. So this cooler tank is where I take the water out to force it up through the solar panels. So it comes out right here. This is the 12-volt pump. You're kind of looking at the end of it here. And then it goes up to the panels. It goes through the panels, and it comes down here into the hottest side over here. Then to connect the two, there's a pipe right here that goes over that connects the two. It basically connects the bottom of this one where the cooler water is in this one to the top of this one. And then the pump takes it out of the bottom of this one. So it's kind of like it completely cycles through both these all day long. And there's a temperature gauge right here that kind of shows you the water temperature when it leaves the tank. There's a temperature gauge over here that kind of shows you the water temperature coming back. And it can get hot. I mean, I've seen this temperature gauge over here at 200 degrees after a long hot summer day with this thing running all day without using a whole lot of hot water. In fact, it gets so hot that if I go on vacation, especially during the winter time or during the summertime, like I was on vacation a couple of weeks ago, before I left, I actually had to cover up the thermal solar panels because if I don't, the water will boil in here. It'll get so hot and it'll blow the expansion valve that's on this tank, the pressure relief valve. It did that once, and that's all it took to learn to do that. So even though we're here in Florida, there's a chance that in the wintertime, we may get freezing temperatures, especially something up on our roof, because it's kind of wide out in the open. So my particular system has two redundant freeze protection systems on it. One of them, I'll just back up a slide here. You see there's a wall wart here plugged in. Well, this kind of goes, it's a very simple circuit, but up on the roof, on one of the pipes, there's a temperature sensor. It's a very specific temperature sensor because if it gets below, I want to say like 38 or 40 degrees, it closes a circuit. When that circuit's closed, it turns this, it turns the pump on with this 12-volt power supply. And it starts pumping hot water, which is, you know, it's hot because it's in here. It's a whole lot hotter than it is outside if it's getting ready to freeze. It pumps this water up through the whole solar system until that temperature sensor warms up to a certain temperature, probably like 40 degrees, I'm guessing. And then it pops off. So it's not like it's running all your hot water through the solar panels all night long. It's just running it through until the temperature comes up to a certain temperature, and then it stops. That's kind of a pretty self-face idea to make it work. The other one is, I really don't have a good picture of it, but there's a bleed valve up on the roof that's designed if the temperature gets below a certain level, it'll kind of open up a little bit. And what it'll do is allow water to flow out, which makes water flow through the system, which kind of inhibits any type of freezing of the water that's up there. Typically that one doesn't go off because the other one works pretty well. So that's kind of the rundown on warming or heating your water for use in your house. The next thing we're going to touch on is heating your house, like heating the air in your house. There's a couple things you can do if you're lucky enough to design your house from scratch and you have a ability to position your house, et cetera, et cetera. There's certain design things that you can do to help with passive heating of your house. This is just one example where in the summer, the sun is much higher than it is in the winter. So this is a good example here where in this particular case, in the summer, the sun would be blocked from going in the window by the roof and overhang on it. Whereas in the winter, when the sun's lower and you actually want the heat in the house, it would shine through the house, heat the house up just because it's shining through the house. But it would also warm, like in Florida, most of our houses are built on a concrete slab. It would also help heat up the thermal mass of the concrete slab so that after the sun went down, you'd still have some thermal mass in there heating the house. That's just one example of some passive heating. You can also have active heating systems. So I designed a couple of those on my house, even though frankly I haven't even turned them on in the last couple of years, but there were a few years where I was using them fairly frequently in the winter. This is one that I designed that's still on my house. Basically, this is pretty simple. This is our master bedroom window, and this is the master bedroom bathroom window. So what this does is it basically pulls air out of the bathroom. It puts it in here, it heats it up, and then puts it in the bedroom itself. And the way it works is this is just an old piece of glass off of which must have been a very tall sliding glass door. I even forget where I got the piece of glass, but I made a 2x4 box for it, and then I put a piece of plywood in the back of it. On each end, this is just a kind of a box inside the box on each end, and these tubes you see that go across here are soda cans with the tops and bottoms cut out and glued together with a high temperature automotive silicone. So these are basically really thin wall aluminum tubes painted flat black. So what happens is the sun will beat down on this, obviously heats everything up in here hot, it heats all that aluminum, and then there's a little solar panel right here that drives a fan that's inside the bathroom window. It pulls air in here, it very slowly pushes the air through here so that air gets hot, and then it pushes in the bedroom window. And actually, it's very efficient. There's a couple other pictures here. This is the outside of the bedroom or the bathroom window where the air comes out of the bathroom and into it. This is inside the bathroom window where the fan's blowing. And I did put an on-off switch on it because if it is warm in there during the day and it's plenty warm enough, I don't want it to get even warmer. So that's just a simple on-off switch. And then this is the output of the system where it blows the hot air into the bedroom. And the air coming in here, I've measured it before, and on a good day, it's like 140 degrees coming into the bedroom. Now, it's not blasting into the bedroom because it's a relatively slow, it's kind of a small fan. If you run the air through the collector too fast, it's not going to heat up very much. So you get a slow flow of very hot air coming into the bedroom. So that turned out, I was very pleased the way it turned out. The next thing on the agenda is talking about even hotter temperatures, solar ovens. And solar ovens, if you haven't seen one work or haven't seen one, basically you're concentrating the sun down into an insulated box and you can get it hot enough to actually cook food. So I've made 3 different versions so far. Each one was better than the previous one. The biggest problem I have with them is most of them I make out of wood, and obviously they're kept outside. So wood outside, no matter how you treat it, only lasts so long in Florida. The latest one I made was solar electric powered, and it was actually self-tracking. It would track the sun with 2 axes during the day. So this is the picture of the first one I made. Sometimes I believe these are referred to as 60-40 ovens because in the summertime, if you want to use it, you can position it this way where it's like a 30-degree angle off the sun because the sun's going to be higher in the sky. And in the wintertime, it's kind of designed so you can flip it so this surface is down and the angle would be angled down further to collect more of the sun. This one only rotates around on a vertical axis, and it obviously does it manually. You have to change it during the day. And this one I designed so these corners would just literally lift right out, and all these sides would fold down in, and then you could put like a cover over it. So, however, what I found was we didn't end up using it a whole lot because it was too much effort to put it together and take it apart. And this is an insulated box with a piece of glass on it. And in the back, there was a door. You could take the door off to put the food in. And then I had handles so you could just rotate it. So that one worked out fairly well, even though we didn't use a ton. So then this is version 2. And version 2, I had gotten a hold of a large piece of glass. It was a pretty heavy duty piece of glass. And it's that old, I don't know if you've ever seen that old style glass. It's got the wire mesh in it. For some reason, I thought this would be a great piece of glass to use for a solar oven, I guess just because it was very heavy duty. So I kind of designed the whole oven around that piece of glass. A couple things I learned on this one, which was kind of interesting, is I had this big piece of glass. So I thought, well, you know, I got a much larger surface area for the sun to beat down in, and so the thing should get hotter. Well, that wasn't quite the thing, because what I found was, yeah, I've got a larger piece of glass. However, I also have a much larger volume in this cooking chamber back here to heat. The other challenge I had with this, which is definitely a learning experience, was there's actually a formula for this angle between the flat glass that's on the front of the oven and the angle of your mirrors that are reflecting the sun in, and how far out these mirrors should go. And it kind of makes sense when you think about it, because if these were more than 45 degrees off the surface, the sun's going to hit them and the sun's going to bounce kind of back out. It's not even going to go in the box, and you want all the sun to go in the box. If they're less than 45 degrees, you kind of waste some of the sun, because the sun's going to hit the mirror and it's not going to spread itself out across the whole box. If you have them exactly 45 degrees, what happens is the sun comes in, it hits it, it bounces over to the other mirror, and it bounces right back out again and doesn't even go in the box. So I didn't figure all that out until after I built this one. So this one kind of worked, but it didn't get super hot. So I kind of scrapped that one, and I went to version 3. Version 3 worked much better. This is version 3. One of the attributes of this one is the box is much smaller. It's very well insulated. These are all at the absolute correct angle to reflect all the sun from this directly into the box. So if this is pointed directly at the sun, every ray of sun that hits this mirror goes inside the box, all the way around. This one also had a couple of electric solar panels on it that ran through a solar charge controller that charged this battery, which was its power supply for both for running the electronics and for positioning itself. The way this tracked the sun was, if you look down here, there's 2 little solar cells with a divider in between them. So I've got a little $3 Arduino Nano board in there in the control system, monitoring the voltage that these 2 generate. If this one's generating more than the bottom one, that means that the sun's hitting this one more than the bottom one. So it moves the whole contraption up until the sun is directly on the edge of this, so both of them are generating this exact same amount of electricity. So these 2 control the tilt up and down, and then there's one here and one on the other side that do the same thing for the horizontal. So when the sun was out and it was nice and sunny, this thing was pointed exactly at the sun, and it worked out very well. This one would get up to like over 300 degrees, so you could cook most anything you wanted to in it. This is a shot of the back of it. This is the door that opened up to put your food in. Down here, the way it rotated was, there's a robot wheel here with a chain reduced gear reduction to a car, or actually a truck windshield wiper motor, 12-volt windshield wiper motor. And that would rotate it during the day as needed. This is the control system, and it's actually not as complicated as it really looks, but this big box here is just the charge controller. Anytime you use solar panels to charge a battery, you really need to run it through a charge controller, because if you don't, you're going to cook the batteries. You're just going to charge and charge and charge and charge the batteries until they're just cooked. So what the charge controller does is that limits the flow of electricity to the batteries, because it can actually determine how much voltage is in the battery, and basically shut the solar panels off whenever you need them. This had there's the Arduino Nano board in there that was controlling the whole thing. I had a digital gauge to show me the battery voltage. This was the on-off to turn the control system on and off. And these were just manual up, down, and left and right. The reason I had those on there was because if it's like noon and the food's cooked and I want to take it out, I need to bring the oven back down to horizontal. So I would turn the tracking off, and then I would bring the vertical down, or I'd bring the vertical adjustment down, so it was horizontal, so you could actually get at it. Some of the other, just real touch on some things. hobby level sensors. You can use solar or light for sensors. Again, we talked about the sensors that I used on the solar oven to position it. You can also use photo sensors, photoresistors. This is just a picture of one, and we actually use these in the introduction to Arduino class. Basically, it changes the resistance depending on how much light's hitting it. So in the Arduino class, we take and put this in a circuit, and if you put your hand over it, like the lights went out, it'll make an LED flash. And again, we talked about the small PV solar cells for sensors. These were the ones I was using on the tracking system. These are only like 1 inch square, and they only generate like 3.5 volts. You could probably power something really, really small with them, but mainly they're used better for sensors. So when I initially wanted to put together a tracking system, I wanted to do it kind of quickly. So the first one I did is I made it out of Legos. And you can kind of see here there's one of the sensors. There's one on the other side. And so this would be the horizontal. This would be the vertical. So this would control the one motor here driving it, rotating it, and this would control this motor, changing the elevation of the angle. So this was actually my first exhibit at Maker Faire many years ago. And again, you'll see solar type things in a number of different toys. You've seen these at the dollar store where the sun hits it and the thing moves back and forth. These are simply a little tiny solar panel connected directly to a motor. So obviously when the sun's not out, there's no energy storage in it, it just stops. Whereas these solar lights that people put along their driveways or their walkways, those have a small battery in them. So during the day, it charges the battery, and then at night it turns the light on, and the light stays on until basically the battery dies. So I think the rest of the class is on to solar electric planning and design. So the first thing they tell you if you want to put solar electric on your house is they tell you you should really start spending money before you even start buying solar stuff. Spend money on making your house more efficient. And some of the rules of thumb that I've seen, at least in the past, were every dollar you spend making your house more efficient will save you $3 on the solar system required to power the energy you wouldn't save if you didn't do that. So some of the examples, some are kind of common sense. Change to energy efficient lights. Make sure there's proper insulation in your house. Make sure your appliances are as energy efficient as possible. Including the AC system. And some of the AC systems they have out these days are extremely energy efficient if you get the very high SEER number on them when you choose one. And then possibly install the solar thermal hot water heating first. And I put possibly there now because since I started doing all this stuff, the cost of solar electric has come down considerably. When I did it, the solar prices were much more than what I paid, or much more than what's going now. Because of that, it made a lot of sense to install solar thermal for your hot water because supposedly the heating element in your hot water heater uses some ridiculous thing like 30% of your electricity is trying to keep that hot water hot all day long. So that justification may have changed now, but it probably still would be a good thing to entertain because it's a relatively simple thing to do. Some other things that you need to keep in mind is make sure your roof is in good shape. When I first thought about putting the solar electric panels on my roof really needed to be replaced. And I knew if I didn't replace it, I would cover the entire roof with solar panels. And then 2 years later, I would have to pull them all off to change the roof. So I did the roof first. Also, make sure you have enough physical capacity in your breaker box. We're going to go through this in much more detail, but you're going to need one or more 220 volt spaces, which is like a double gang space in your breaker box. You're either going to need a couple of those. You're going to need a minimum of 2 of those, probably, depending on what type of inverter you use. When I bought my house, it had an old Federal Pacific Electric breaker box in it that apparently they had been recalled, but most of the people in my neighborhood who owned the houses before we did never had them swapped out. So it was kind of funny, because when I first moved into the house, I'm like, okay, well, I want to add a circuit to the garage because that's my workshop. So I went to either Lowe's or Home Depot to buy a breaker, and the breaker for my breaker box was in a special locked plexiglass cabinet in the store, because the thing was like $45 or $50 for a stupid 15 amp 110 volt breaker. So anyways, I replaced all that and put a very large square D breaker box in, where the breakers are, $5-10. Again, going on with the electric solar energy for your house. Basically, when you generate the electricity, it goes into the electrical system of your house, and then if you generate more than you use, it goes back into the grid. So the electricity you generate is basically used for anything you use at your house. Obviously, the solar electricity is generated from solar panels, and the technical term for it is photovoltaic. Photo meaning light, and voltaic meaning the volts part of it. A lot of times that's condensed down to PV. So a lot of times it's referred to as just PV panels. One challenge we have with it is the power that's generated off the solar panels is direct current. Kind of like portable electronics, like your car's direct current, your phone's direct current. Most anything that's portable is on direct current. However, everything in your house normally operates at alternating current. So we have to convert this direct current into alternating current so the things in your house can use it. And the device that's used to do that conversion is called an inverter. And you've probably seen inverters before. We'll go through that in just a minute, but there's pretty much just 2 main parts to a solar electric system. There's the solar panels that generate the electricity, and the inverters that convert it into alternating current. It's electrically, it's a relatively simple setup. So talking about inverters, you've probably seen these ones like you can put in your car. You plug in your cigarette lighter, and all of a sudden you've got a fairly low power or low current 120 volt circuit, like charge your laptop or your phone or whatever. This one is a little bit larger one. The same deal though. This one is large enough where you wouldn't be able to plug it directly into your cigarette lighter. You'd have to wire it directly to the battery. But this would power a lot more, a number of more things with a higher wattage than the small one. So the ones we use on a house basically do the exact same thing. It's just they're a little more heavy duty. They're weatherproof because a lot of them are outside, and they're designed for a very, very specific purpose. So, and when we talk about the inverters on a residential system or your house, there's 2 methods of doing it, or 2 technologies to do it. They both kind of do the same thing, but they just do it in 2 physical different ways. The first one is what's called a central inverter. A lot of times it's called a string inverter. That's basically one inverter. So all your solar panels get wired back to this one box, and the box converts it all to alternating current. The solar panels are normally connected in series, which means they're solar panel 1's connected to solar panel 2 to 3 to 4 to 5, all the way to say 10. And that string of say 10 panels is wired back to the inverter. And then you do another string and another string. Normally when the system is installed, there's only one central inverter for the system. And the entire system kind of functions as one generation unit. If you have multiple strings or multiple rows of panels on your roof, it kind of separates out a little bit into different generation units, but it's kind of all one generation unit. We'll get to that in a minute because there's some disadvantages to that. The other way of doing it is what's called microinverters. And microinverters do the same thing, except you put one behind every panel. So the panel generates direct current. It's plugged directly into this inverter, which immediately converts it to alternating current, and that goes into your house. So there are a number of advantages with that. So each panel, like I said, has its own inverter. Each panel / inverter is a separate generation unit. And we'll be going into that in a minute, some of the advantages of that. And the microinverters, I have microinverters on my house, and the microinverter company that I use is called Enphase Energy. And Enphase Energy, I'm not sure if they invented the microinverter, but they have by far the most the largest market share. In fact, they have 36% of all inverter sales in the United States, not just microinverters, all inverters put together. So if you want to see what they look like, this is a typical string or central inverter. It's one big box. Many times these are they're designed to be waterproof, so they can be either mounted in your garage or inside somewhere or on the outside of the house. I've seen them both ways. This next to it is a microinverter, and this is a typical Enphase. They kind of have different models. They look a little different than this now, but this is a typical Enphase inverter. And this thing, you can't really tell, there's no real gauge on it, but it's probably about 8 inches by, say, 10 inches tall, somewhere around there. And it's only about 1 inch thick, so they're pretty small. So if we look at the way the two different systems are wired, the top system here is for a centralized or a string inverter. And the way they're wired is, like I said, number 1's wired to number 2, that's wired to number 3, all the way through and to the whole first string, and then the string is sent back. If you have a number of panels, there may be multiple strings of these wired back, but each string itself is wired in series. So it goes through one and through the next one, etc. On a microinverter, it's a little bit different because you've got the panel, and then literally underneath the panel, you've got the microinverter, and the microinverter plugs into a cable. So this is just one long cable that goes from your breaker and your breaker box up onto the roof, and these kind of things you plug in as you go along. So we'll be looking at this again because there's some advantages and disadvantages of both. So if we look at the string inverter first, a couple of the pros that are on a string inverter is the first one's a cost. So I went online and did some quick looking, and a 5 kilowatt string inverter goes for somewhere around $1,300 if you bought it yourself. Obviously, if a solar installer is going to install, they're going to mark it up, but right around $1,300. For an equivalent system for 5 kilowatt system for microinverters, it would be $3,000. So your upfront cost is definitely more for microinverters. That's why if you ever have any of the people walking around your neighborhood or calling you or whatever, when they give you a quote on a solar system, it's almost always going to be a central or a string inverter, just because they want it to come as least expensive as possible. There is, I'm not sure this is really a pro or not, but I put it down here. There's less electronics to fail. There's one central group or central box of electronics. The problem is if it fails, the whole thing's down. If we look at if we start looking at some of the cons of a central string inverter, the first one is typically they have around a 10-year warranty, or microinverters have a 25-year warranty, and just about all solar panels have a 25-year warranty. So it is an advantage warranty-wise to go with microinverters, because the inverters have the same warranty period as the actual solar panels do. Another con is if one panel in a string has a production problem, it affects the entire string. So if we go back and we look at this wiring diagram again, electricity goes through this, goes into the first panel, through the first panel, the second panel, et cetera, et cetera. And if you think of this, pretend this was water for a minute, and this was a hose. If the hose is kinked anywhere along this line, it's going to slow the water down going through the whole thing. Well, the same thing happens with electricity. So if something's wrong, or something's wrong in any part of this path, it's going to slow the electricity down going through the whole thing. So an example would be is if one of these panels were to go bad, you might lose this whole string of panels because now there's an open in the circuit and electricity can't even flow through the whole thing. Another another way that could be affected is, let's say that you've got a whole bunch of these down your roof, and say at noon when the sun gets to a certain point, there's a tree in the way and it actually shades, say, the last one. Well, that's going to slow the flow of electricity through the last one, which slows the flow of electricity through all of them. So you kind of, that is one disadvantage of the string inverter. Another kind of disadvantage is the voltage and current that's on your roof is substantial. Most of the time they require a DC disconnect switch before it gets to the inverter for a kind of a safety code type thing. And if we go, again, we go back and look at this, each one of these panels will generate, say, 30 some odd volts. So if you have 10 of them in a row, now you have 350 volts at a decent current in this wire. And if anybody's ever played with, or not played with, but like dropped a wrench or a screwdriver on your car battery, and it'll just melt the thing, whatever hits it. That's a good example of why this is slightly dangerous to have that that level of current and voltage on your roof. Another con is any maintenance work that would need to be done on it is more difficult than a microinverter. I say that, but there's one big section of the centralized inverter that you're, as a consumer or as a non-employee of the company that made it, you're not allowed to go into. Same thing with a microinverter. You can't get into a microinverter. However, it's much more easy to replace a microinverter. You just unplug 3 things and plug a new one, and anybody can do it. You don't need an electrician to do it. Whereas if your centralized inverter goes, you would, depending on your skill level, technically you have to have an electrician to replace it, because you have to disconnect the feed from the breaker box and then disconnect the feed that goes up to the solar panels. And one other kind of a con to it is, if you want to upgrade your system, say you decide you wanted to, we'll use our 5 kilowatt system. Say you wanted to put that in your house. So I want a 5 kilowatt system. So the company sells you a central inverter that's 5 kilowatts and 5 kilowatts full of panels. Well, if you want to make the system bigger, well, now you have a couple choices. One choice is you can replace that 5 kilowatt inverter with a larger one and then just add more panels to it. Or what most people do is they'll just buy another central inverter and start populating that. But so you kind of need to do a little more future planning on it, because you kind of want to know your wildest dreams and kind of plan around that. The microinverters, it's much easier to add additional panels and inverters in the future, and we'll be going over that. Let's see, I think there was one more. Yep. This is another, in my opinion, disadvantage for a string inverter is, since the panels are configured in strings, you really cannot monitor the individual panels. So if something goes wrong with one of those panels, somebody's going to spend some time unplugging them all and putting a meter on each one of them to see where the problem is, versus having some type of automated software system that says, hey, this particular panel right here is having a problem. And you can actually do that, and I can show you. You can actually do that with the microinverters, because they monitor right down to the panel level. Now, some companies are getting around this or helping with this by installing some type of module at each panel, but then you're kind of going in the direction of microinverters with having something on every panel. So again, we go back to the microinverters, where you've got a microinverter behind every panel. And some of the pros, it's a very simple design and installation. The way the system's designed, I just pulled this off the internet, is it's actually pretty easy. If this was your breaker box in your house, this would be a breaker you would install to put your first string of solar panels on. This breaker is just a standard 20 amp, 220 volt breaker. This one actually shows a disconnect switch. Here in Florida, we don't need disconnect switches on a microinverter system. So basically, you install a breaker in your breaker box. You run 4 wires of the appropriate size up to a junction box on the roof. Then there's a cable you buy, and if, again, this is pretty much all based on N-phase microinverters, but it's kind of the same with most other inverters, microinverters, is you buy a cable from N-phase that has a connector at every panel position. So if you want to install, like, say, 10 panels, you buy a cable that's got 10 connectors on it. Then what you do is you go to the first panel. You take the panel, you plug the panel in the inverter, the microinverter. You plug the microinverter in the cable. You do that 10 times. You turn the breaker on, and you're done. That's it. And to kind of show you what it looks like, so this would be that junction box on the roof. So we'd have 4 wires coming from the breaker in your breaker box up to the roof and tie into the end of this N-phase cable. They call it N-phase trunk cable. So you get to the first panel, you would take the inverter, you just snap the connector right into that cable. These 2 connectors connect to the 2 connectors on the solar panel, and you're done. If we go back one to this, on a particular one of these circuits, you can put 16 microinverters on one 20 amp breaker. So if you started with 10 and you come back a year later and say, you know, I'd like to add 6 more, all you do is turn that breaker off, go over here, you find the end of this cable, and you buy a connection kit that basically connects the end of this cable to the other 4 position cable or 6 position cable that you bought to keep going. And you just go to the next one and plug the inverter in, you plug the panel in, you know, 6 more times, you turn the breaker back on, and now you've got 16 panels instead of 10. That's pretty much all there is to it. Again, this is the only demo I actually do during the actual class, is I actually show you how to plug it together, but it looks just like that. So again, some of the pros of the microinverters, again, it's very simple design and installation. It's very simple and straightforward to expand, like I've talked about. They do have the longer warranty than a central inverter, the 25 years versus the 10 years. And each panel or inverter combo is its own power generation unit. So if there's a problem with one panel, it only affects the one panel and one inverter. The other ones don't know or don't care. Again, the monitoring is right down to the panel level, or right down to the inverter level. And the panels can face different directions. When you think about the string inverter or the central inverter, you'd really want all those panels facing the exact same direction. Because let's say you had 10 panels and 5 of them were facing, say, south, and 5 of them were facing east. Well, the sun's never going to hit all of them at the same intensity, and even if it does, it's not going to be at the ideal intensity. So you're never going to have an ideal output of that string. So that's why they always have to plan out. There's a lot more planning involved with a central inverter than with the microinverters. With the microinverters, if they're facing different directions, the one doesn't care what the other one does because they aren't connected together, really. And it is okay for an individual panel to be shaded because it only affects the one individual panel. It doesn't affect any of their ones because, again, they're all individual generation units. And there's only a couple of cons with the microinverters. One of them is obviously, like I mentioned before, the upfront cost is more compared to a central or a string inverter. And if one of these inverters were to fail, remember they're usually bolted to the mounting rail behind the panel. It might be difficult to get to. So one of the examples, if you look at this particular example, if this very central inverter were to go, or the panel were to go, you'd obviously have to remove at least 2 other panels in order to get to it. You just kind of want to keep that in mind. Now, that's kind of if the inverter goes. If the panel goes, it doesn't matter what type of inverter you have, you still have to get to that panel. So let's talk about solar panels themselves, the actual panels themselves. Most all of them are the same physical size. They're roughly 66 inches tall and 38 inches wide. And one of the reasons most all of them are the same physical size is because the majority of the rails you mount them to are typically in 10-foot lengths. It's just a standard length for a lot of things. So you want to be able to put 3 of them on a 10-foot section, so that's why they're 38 inches wide. It's 38 inches times 3, plus you want a little room in between them for the mounting brackets to be able to secure them to the actual rails. They vary in power. They're getting above, commonly above 340 watts now, but most of the ones you'll find on for sale are somewhere between 280 and 340 watts. When you go to select a solar panel, there's really only 3 things you really need to keep in mind. One of them is the output of the panel should match what the inverter is rated for. So most of the inverters I have are the M-Phase M250, which are designed to work with panels that are anywhere between 210 watts and 340 watts. You could put a larger wattage panel on one of those, but you'd be kind of wasting some of that wattage of the panel because it's going to be going through a 250 watt inverter. So that's one thing to keep in mind. Another one is that they make 2 different types of solar panels with the number of cells that are on them. And if you look at a solar panel, you can see the squares or the rectangles all over them. Well, there's either 60 of those things or there's 72 of them. Most of the time for residential use, they're just about always 60. The 72 cell panels are the same width as a 60, but they're a little bit taller to add those extra 12 cells on. And the only place I've really ever seen those is commercial settings. Like when you go by a field and they're full of solar panels, they always use 72 cell panels. I think they also use a lot of them on commercial entities where you want to get as much electricity out of a single panel as you can. So they use 72 cell panels. And the only reason I bring that up is if you're going to buy any type of used inverters, especially N-phase inverters, some of the older ones only handled 60 cell panels, whereas the newer ones they don't care. They can handle 60 or 72 panel cells. So again, if you're going to buy some used or new microinverters off eBay, just kind of keep that in mind. And then obviously the connector type on the panels needs to match the connector type that's on the inverter so you can actually plug it into it. The vast majority of panels come with a connector type that's called MC4s. It's kind of like the industry standard. However, if you do get a good deal on a pallet of old or even new panels and they aren't MC4s and you've got a bunch of MC4 inverters, for like 25 bucks, you can buy the crimp tool, and the MC4 connectors themselves, you can get off of Amazon for like $2 a pair. So it's really not that big of a deal because it's so easy just to crimp on whatever type of connector you need. So the next thing for the planning is trying to figure out where we're going to put the panels. So there is there's obviously different places you can put them. The roof is by far the most common because it's off the ground, it's out of the way, and a lot of people don't have any other place to put them. You can also ground mount them. If you ground mount them, you can typically, if you have the room to do it, you can typically make sure they're faced exactly south, which helps. And you can also control the elevation of them, how they're tilted. And in Central Florida, the ideal tilt for year-round production is at like 25 degrees. And then if you want to get carried away, like I did a little bit on some of mine, is you can install a tracking system. Because if you can keep the solar panels perpendicular to the sun all day long, they're more efficient. which kind of makes sense. Another thing to keep in mind for planning is shading. Are there any trees near your house is going to shade part of the roof that the solar panels are going to go on? I just chopped all the trees down in my backyard that were going to be in the way of any solar getting to my roof and didn't worry about it. And then the azimuth. And the azimuth is what direction the panels are facing relative to south. So you may have one side of your house faces north, one side faces south. Obviously, you want to put them on the south side. If your two sides of your house face east and west, it probably isn't going to make a whole lot of difference what side you put them on. However, the next slide, we're going to talk about a little bit more about some detail of the planning for that. So the government has this pretty cool website out here called pvwatts.nrel.gov. And what you do on this tool is you put the address of your house in, you put the system size in watts of the system you're planning on. You put the array type, whether it's fixed or whether it's 1 or 2 axis tracking. You put the tilt, which if you're going to mount them to the roof, that would be the angle of your roof. And the azimuth, which is if you're going to put them on the roof, the direction that part of the roof is facing. And it spits out. If you also put in there the how much you pay for electricity, typically in Florida it's around 13 cents a kilowatt hour. It'll tell you right down to what your monthly production should be in dollars as well as the watts it should generate, and it is relatively accurate. So that's a pretty good resource. So let's now switch gears a little bit and let's talk about batteries, because a lot of people that think solar automatically think that every solar system has to have batteries, and that's not the case. During a power outage, if you don't have batteries and the power goes out, you don't have any power. And with solar, and the reason for that is there's a safety feature in all inverters made that senses the incoming voltage, basically the voltage from the grid, and if it sees that power is lost, it shuts the inverter down. And the reason for that is if that safety feature wasn't there and everybody in the neighborhood lost power and you're still generating power, it's shoving a whole lot of power out on the power lines. So when the poor lineman goes out there to start doing work, all these lines are going to be energized when they shouldn't be. So it's a safety hazard. So they're all kind of all designed that way now. Now the latest version of the inverters that Enphase has gets around that a little bit, but to me it's kind of a hokey setup. It allows you to get power to 1 or 2 receptacles in your house, and that kind of depends on how much sun is out. So if the sun goes behind a cloud, it's going to turn those off until the sun comes back on. So you really want to put like your desktop computer plugged into it, or even your refrigerator, because it's going to be going on and off throughout the day. So let's talk a little bit more about batteries. Batteries can be really cool, and they can keep your power going during a power outage, obviously. Now, depending on where you live and the power outages you get, can play into how much you want to spend, if anything, on batteries. My power at my house does not go out very often, and does not in any way close to justify buying batteries. And we'll kind of go into some pricing here in a minute. But however, some areas can use the batteries to help you save money in parts of the country that have peak power rates. And I know like California has peak power rates. So you can kind of use the battery power that's or the electricity that's in the battery to tide you over during those really high peak power rates, like say during noon or things like that. One thing to keep in mind is that if you have batteries on your solar system, they do not operate like an uninterruptible power supply. If you've done much work with computers or servers or network equipment, a lot of those are plugged into UPS battery backups, and those are specifically designed so if you lose power, the computer or the equipment that's plugged into it never knows. So if you have batteries on your solar system and you lose power, typically there are automatic transfer switches in place to transfer it over to the battery. However, keep in mind it's still going to be electrical outage to everything in your house. It's going to be like there was a power glitch and everything's going to go down and come back up again. Batteries are kind of expensive. So my 1,300 square foot house can use up to 30 to 40 kilowatt hours a day during the summer, like when the AC is running quite a bit. So if we do some simple math, and I did some research on the Tesla Powerwall, and it's relatively priced fairly competitively with the old style battery systems that are out there. So again, this information may be like a year old or so, but at the time, a 13.5 kilowatt hour Tesla Powerwall 2 battery pack had a list price of $6,700. So if you look at that 13.5 kilowatt hours, let's say I wanted to be able to run my house for a day. Well, I'm going to need at least 3 of those. So 3 of those would be $20,000. And keep in mind, if it was like during a long power outage with bad weather, like say we had a slow moving hurricane that came through, so that would power my house without any additional charging from the solar panels for 1 day. So that's $20,000 to power my house for 1 day. You know, I may, if there was some sun or whatever, I may get 2 days out of it. That's it. And depending on the chemistry of the battery, the typical battery lifespan is only 5 to 15 years. The 5-year end would be more like the old lead acid batteries, like the car type batteries. And then the 15 years would be more like the lithium ion ones that are in the power walls. You're still, after that time, you're still going to have to replace the battery. So that's obviously not another 20 grand, but it's still many thousands of dollars. Alternatively, it's not quite as green. However, you can buy a nice whole house home generator for about $5,000. And as long as you keep feeding fuel into it, it's going to keep going. It's going to power your house until it comes back on. So if you have to have power at your house and you have power outages all the time, I would seriously consider looking at a whole home generator versus batteries, at least at this point in time. So if we look at just the overall cost of a solar system, I pulled these off the web, and the average installed cost in the U.S. is right around $3.14 a watt. For a 5 kilowatt hour system, it'd be around $15,770. That should actually be 5 kilowatt system. That's 5 kilowatt. Yeah. There's no hours there. If you did it yourself, it's somewhere around $2 a watt because you save quite a bit of labor putting everything together in the markup from the vendor. So that's somewhere around $10,000 to $11,000 for the same 5 kilowatt hour system. Now we currently are under a federal tax credit for solar purchases, and this is the rundown. For several years up until last year, up until 2019, there was a 30% tax credit. This year, there's a 26% tax credit, which still isn't bad. And then it slowly goes down after that until 2023 and forward at 0. Now, obviously, this is what's currently in law and currently passed, and this could certainly change. I wouldn't think they would get rid of this. However, depending on how the politics goes over the next several years, this may change. I mean, they may renew it right to 30% again, you know, who knows. One thing to keep in mind for this is I'm not an accountant. However, this is a tax credit. It's not a tax deduction. So if you spend $10,000 on a solar system, when you do your taxes last year, you would have gotten $3,000 back. It's not a deduction. It's actually a tax credit. Also, in the state of Florida, any solar related stuff you buy, whether it's solar thermal or solar electric, it's exempt from state sales tax. Also, these federal tax credits also apply to thermal solar as well. It's thermal solar and PV or electric solar. So if you want to do it yourself, like I did, here's some of the steps that I went through. And just as a, not really disclaimer, but is a little more detail, these steps are written for what I did. So what I did was state of Florida, obviously. I live in unincorporated Orange County. I don't live in a city. And I have Duke Energy. Some of these will change depending on where you live and who the jurisdiction is and what power provider you have. So step one is you got to plan the size and where you're going to mount it and how you're going to mount it. Then what you need to do is you need to have the system drawn up and signed off by a structural engineer. The Makerspace actually has a couple of PEs that are members that I learned that would have the ability to sign off with the proper circumstances. I just happened to, my background is in engineering and physics, so I did all the wind load calculations, I did all the drawings and everything else, and the construction related work I do at the hospital, I actually knew some structural engineers. So for the price of lunch, I had one of them have their company put all my information on their drawing format and sign and seal it for me, which was great. Then again, if you own the house, you can be your own general contractor, so you can go down and pull a permit. So I went down and pulled a permit with a local agency. In my case, it was Orange County. This is one that I missed that I can kind of kick myself, but and to me, it's frankly kind of a racket. But there is a organization in Florida called the Florida Solar Energy Center. It is a division of UCF. And I guess to help sustain their existence, every system that is installed in the state of Florida has to be certified by the Solar Energy Center. So what you do is you send all your drawings and $250 to the Florida Solar Energy Center. They look in and send you a letter back that says, yep, looks good. Then you need to install the system, and then you need to have an electrical inspection come out. And at least with Orange County and my experience with Orange County, if you've done a good job and everything's nice and neat, they're just going to glance at it and know that you did a good job. So that's what happened with me. And then the last step is you take the paperwork from the power company. Like Duke Energy has this form you have to fill out, and the bottom of the form has to be signed by the electrical inspector, basically saying it's cool. And then what they do is, at least if it's Duke Energy, their process is they swap your meter out for one that goes forwards and backwards. So the meter they gave me is basically it's a commercial meter that's on commercial buildings. I think the only reason they use a commercial meter is because it can actually run backwards and they keep track of that. If you have a different energy provider, they may do something different. Like I know OUC, Orlando Utilities Commission, in the past, the way they did it is they installed an additional meter on your house to track the amount of electricity that you've produced. So the one would turn forward and the other one would turn backwards, and they would subtract the two to figure out how much to charge you. So if we look at my system specifically, in my current system, I currently have 67 solar panels, which is a lot. It's currently around a little over 16 kilowatts. I have 40 panels mounted on my roof, and I currently have 27 panels mounted on 3 two-axis tracking systems that I designed and built. Because there's so many panels, they are on 6 20-amp circuits. So when you kind of think, if you want to go big like I did, you're going to need, like those 6 20-amp circuits takes up 12 breaker spots in a breaker box. It's quite a bit. My annual energy production is 19,000 kilowatt hours, which is more than I use. And the amount of money I've paid Duke Energy over the past 36 months is nothing. Because what happens is, again, this is Duke Energy. The way Duke Energy works is at the end of January, if I've generated more than I've used, like say I've generated 100 kilowatt hours more than I used, well, they put that 100 kilowatt hours in a bank for me. And then it just so happens every month I always generate more than I use. So let's say February comes around and I generate another 100 kilowatt hours more than I use. So now I've got 200 kilowatt hours in the bank. When it gets to December, if I still have money or still have watts in the bank, they pay me for those. However, they don't send me a check, they credit my bill. However, there's like a $10 a month fee on all of our bills, specifically for a connection fee to the grid. So the way mine works is when I get to the end of the year, I've generated enough electricity, and the credit they give me is more than $120, which takes care of the 12 months of $10 a month connection fees for the next year. And you might ask, well, how much do they credit you per kilowatt hour? Typically, it's right around 3 cents a kilowatt hour. And some people, I've heard gripe about this, like, well, you know, I pay 13 cents a kilowatt hour, and if I generate more than I use, they only give me 3 cents a kilowatt hour. Well, part of that is because part of that 13 cents a kilowatt hour you pay the power company has to do with all the maintenance of the entire infrastructure that you're using. And like at night, I'm still using all their power lines. I'm still using all their, every part of their system I'm using at night because I'm not generating electricity. I'm just making the meter run backwards more during the day than it runs forward during the night. So that's the way that credit kind of works. This is a picture of the back part of one part of my house. This is the thermal solar we talked about, and this is one set of panels kind of on this end of the roof. There's more on the other end of the roof. This picture is the one, I think this is the exact picture that's used in the class advertisement. These are the three 2-axis tracking solar arrays in my backyard. And to be honest, what I'm doing actually as we speak is I'm converting these to a straight ground mount. I ran into a couple issues with these. They work quite well. They're very accurate. However, the two biggest problems I've run into with them is it's a mechanical system, so it takes some maintenance, which isn't that big of a deal. However, for instance, the linear actuators, the thing that make these things tilt up and down, I'm having a hard time finding ones that are anywhere near affordable that will actually last. So I'm constantly having to take these things apart and fix them. I mean, this one I had to change bearings out in it once. These other ones I have to keep changing the brushes and the motors out because they really aren't designed for exterior use in Florida. However, my biggest gripe with these is when we have a tropical storm, I design these so they can lay flat. I flip them all the way up so they're flat. And then when I poured these concrete donuts that the wheels ride on, I poured in metal loops all the way around. So basically you lay it flat and you tie it down to the metal loops, which seems to work very well for tropical storms. However, I really wouldn't want these out there during a hurricane because who knows where they would end up. So during a hurricane, I have to take them down, which is a real pain in the butt. So I had to take them down last year. I obviously didn't have to, but I ended up taking them down anyways because that storm we never got really. However, I'm sick and tired of doing that. So I'm going to ground mount these kind of like this direction right here. And last weekend, I just got done pouring the 10 concrete footers to do the mounting on them. I do have a video on my YouTube site that explains exactly how the whole tracking system works. I have modified the tracking system since the video was made, and it's actually even more accurate now. But again, I'm kind of rearranging all that. This particular part of my house is an addition I built on here myself. And it just so happens to open up some more real estate for me to put more solar panels. So what I have on my roof, I should have explained that before. What I have on my roof is what's called a standing seam metal roof. And the way it works is kind of cool because you start with the first panel, and it has a seam that comes up, over, down, and then there's a tab all the way up. The tab has holes in it. So what you do is you screw that tab down, the next piece snaps on top of that one, and you screw that the other tab down, and just keep going. And when you get done, there's no penetrations in your roof, so it can't leak. There's no way the water can get through the metal to leak into your house, which is great. Another advantage it offers is now you've got this structural ridge or seam that you can actually bolt things to. So it's kind of hard to see in this picture, but there's a company out there called Z something, I forget the name of them, but they sell these aluminum blocks with a slot milled in the bottom. You set the slot over the standing seam in the roof, and there's a set screw in the side of it. You tighten up, and now you've got a block secured to your roof that will not come off. And in the top of it, there is a threaded hole that you can mount anything you want to. So in this case, I've got all these blocks on here, and then I've got the rails mounted to the roof. And all these are mounted to the roof, and there isn't a single penetration in the roof. So that's kind of step one if you want to do it in this method. If this was a regular asphalt shingle roof, instead of using these little blocks, they make flashing pieces that you bolt down, you lag bolt down into your roof trusses. So that's step one. Step two is, this is step two. So now I've got the cable run and all those inverters mounted to the rail, ready to accept the panels on top of each other, top of each one of them. And then lastly, these are the 21 additional panels I put on my roof when I put the addition on. Because there's 21, those have to be on 2 circuits. And I'm sorry, I actually just figured out that one of the little things that keeps lighting up every once in a while is the chat window. So sorry about that. I'll get to your questions in a minute. I'm sorry, I kind of meant to do them as we went along. I only have, there's only 6 more slides here. So if we look at the finances of mine, and again, this was the original setup that I put on there, which I think was the 40 panels, or which was roughly a 10 kilowatt system. So these are the numbers here. So what the total system cost me after the tax rebate was right around $15,000. And if you, at the time, I was generating about 1,937. I'm sorry, if you look at the number of kilowatt hours I was generating, I forget what it was now, but you times that by 13 cents a kilowatt hour, and I was saving about $1,937 a year because they have to pay for electricity. The ROI in time is 7.7 years. So if you divide that out, it's going to take 7.7 years to pay for itself. So that's kind of cool. This is the first house I bought, and I'm planning on being the last house I ever buy. So I'm good with staying here. However, the way I really rather look at it is if you had $15,000 and you invested it, and every year you got $1,937 back, that's a return rate of 12.9%. That's pretty much guaranteed for 25 years because every part of the system is guaranteed for 25 years, which is kind of cool. I'd rather look at it that way. There isn't much else out there that you can say, hey, I'm going to invest money and I'm going to be guaranteed 13% return on my investment for 25 years. And if we look at my power bill, and this is, if you have Duke Energy, and I need to update this because the power bill looks a little different now because they made it more user-friendly. But this is from last February. And so I've highlighted the numbers that really only mean things. So this is my current bill, and this is what my bill is every month for power, the $10.90 a month connection fee. That's just these 3 things added together. If the line below it, it might be a little blurred because of the highlight, but it says net metering annual unused energy credit. So this was the credit I had left over from the previous year. I had $87.57 credit from last year. No, I'm sorry. The next one down, the credit balance, I had $50 left over from last year. February is the bill that they credit you the previous year's credit on. So on this particular bill, I was credited $87.57 from the previous year. And if you subtract the $10, that meant at the end of February of last year, I had a credit balance of $126, which was much more than enough to pay the rest of the bill, rest of the year, the $10 a month connection fee. If we look over on the other side, there's all this on-peak, off-peak stuff. The first bill I got from this, I was totally confused. I actually had to call Duke Energy, and because my bill now is 2 pages long. But the only reason it's 2 pages long is because, remember I said they swap a meter out for one that's a commercial meter? Well, if you're a commercial entity, you pay on-peak and off-peak and all sorts of weird stuff. So when I went through this with the person from Duke Energy, they were basically said, this line means nothing to you, this line means nothing to you, this line means nothing to you, and kind of on down. But the thing here is that the key here is the total kilowatt hours. So this is the amount of kilowatt hours that my meter moved forward during the month. It's kind of it's a little bit irrelevant because they have no idea how much electricity I generated. That's how much the meter moved forward for the month. If we go to the next page of the bill, this shows how much the meter went backwards during the month. So during that month, they received 771 kilowatt hours. And right now in the bank, I think this is the last month that I actually generated less than I used. So what I have in the bank in February of 2019 was 701 kilowatt hours in the bank. So every month I get the bill and this number keeps going up and up and up. I'm one of the very, very few people you'll probably meet that looks forward to getting my power bill every month because I actually log it. It's like, oh, now I'm up to this much balance. So that's the way my power bill works now, or lack thereof. So remember I talked about the microinverters and how you can monitor each microinverter itself. Well, the way it does that is this device from Enphase called, it's called an Enlighten Gateway. It's a pretty simple box. All it does is it plugs in the wall and you connect to the internet, either wirelessly or you plug a network connection into it. And it's kind of cool what it does. Every 5 minutes, every one of my 67 inverters reports to this thing, and this thing sends it up to the web and puts it on my portal on the internet, on their website, Enphase's website. It just does that all day long. That's the job of this thing. And this thing's kind of expensive. I think they're like $600, but you only have to buy one for all your panels. This is my portal for Enphase. So this is a graphical layout. Let's see if I can make it bigger here. This is a graphical layout that I made of all my panels. So this is the initial part of the house. The thermal solar panels are in this area here that's kind of carved out. This is the 21 panels I put on the addition, and these are the 3 9-panel tracking arrays. And it does, this is the summary page. So what it does is it shows you that today I've generated 32.9 kilowatt hours. That's not that great because it was cloudy a lot today and it rained all afternoon and it's just been kind of a crappy day. The past 7 days I've generated 375 kilowatt hours, and the month to date I've generated 1.6 megawatt hours, or 1,600 kilowatt hours. Lifetime of my system, I've generated almost 80 megawatt hours. This is the overall microinverter AC voltage, which I guess that's good. I don't know. The question is, what are the dark sections on the control panel? So these, if you look at these, it's kind of weird. The lighter the color means the more that panel has generated today. So these two haven't generated a whole lot, and the reason these two haven't generated a whole lot is because I have this array disassembled, because remember I told you I was going to ground mount these. I have this array disassembled. I have some sawhorses set up in my backyard with some bars between them, and they're just setting on that bar. And a couple of these are kind of behind this array, so these are probably shaded, so that's why probably those aren't. These two, For some reason, these two microinverters aren't reporting right at the moment. And sometimes when the solar when the sun gets kind of dark, sometimes they'll stop reporting for a little bit and then start reporting again. But if we choose any one of these, this is the serial number of that inverter. So if I click on here, it'll go in, it'll tell you how much that inverter is generated today, how much it has the past 7 days, month of date, lifetime, etc. And you can kind of compare that to some of these. This one, I think I have an intermittent problem with the actual panel. So you can see that today this generated 556 and these 560, these are pretty much the same, but this one only generated 293. So something's up with that one, but it still is generating. So if I go back, if you really want to get into this, if you click on one of these, it'll comes up with this little graph thing. If you click on the graph, it gives you all sorts of information about the actual inverter. So this is the power over the last few days. So obviously down here, when it doesn't generate a whole lot, that's at night because it's not generating anything. These peaks, it's kind of interesting because if you're into meteorology, you can see that at my house, you can see exactly when the sun was shining and exactly when the clouds went over, because that's what all these ups and downs are. If it's a sunny day with no clouds, this is almost like a perfect bell curve. It'll go up and it'll come back down. That's it. However, you know, we're in Florida and it's summertime, so you rarely get an all sunny day. You on here, you know, you can get anything. I mean, you can go to reports and then go site energy production, and I'm just going to go like you can go in January 1st to yesterday, and it'll tell you how much you generate every single day. You can kind of tell what the good days, what the bad days are. I mean, you can see there's a 70, which is pretty good. The most I've ever generated has been 92 kilowatt hours in one day, which was quite a bit. And believe it or not, it's kind of weird. In Florida, your prime production days is like March and April, which you wouldn't think. You think in the middle of summer, you know, when the sun's the highest. But when the sun's the highest in Florida, well, that's when we have all the storms. So. The one other thing I wanted to show you was this is my solar arrays when they were all functioning, everything. This is a typical time lapse of a day, them tracking the sun all through the day. So it's kind of cool when they're all working and things. And then at like 8:30 at night, it would just reset itself back to where it was. If you want to mess around with solar and you don't want to do all this inverter stuff and you just want to mess around with like DC for batteries, or you've got a camper you want to mess around with, whatever, a great thing to get just to start out with is Harbor Freight has this system where it has 4 25-watt solar panels. It has a charge controller. It has some 12-volt light bulbs you can hook onto it. It's got all the cables to hook everything together and the cables to hook to a battery. It doesn't come with a battery, but if you were to connect this to a battery, you could have a solar system charging a battery all the time, and then you'd have 12 volts on the battery that you could do whatever you want. And obviously, you can always get a 20% off coupon for Harbor Freight and get $40 off this. So I always bring that up if somebody wants to mess with stuff, but they don't want to go full blown on some house alternating current thing. This is a cool thing to play with. And then the last slide on here just has some of the resources that I had mentioned. This is the company that makes those long, skinny, relatively lightweight thermal solar panels out in California that I bought. This was the website for that planner from the government that works pretty well. This is the Florida Solar Energy Center, and other than taking my $250, there actually is some good information on their website. And I throw this in here. I have absolutely nothing to do with this company. However, when I bought most of my solar stuff, I bought it from a company called RES Supply out of Colorado. And one of the reasons I bought it from them is because they have, for a minimum order, there's no shipping charge. However, the interesting thing about solar panels is because of the size of them, you can't ship them FedEx or UPS. They won't take them because they're too big. So they have to be truck shipped. You know, they have to be shipped freight. Well, that can be pretty expensive. However, this particular company, anything you have shipped, there's a $149 flat rate if it has to be freight shipped, like solar panels. So you could order two pallets of solar panels from them, and they're only going to charge you $149 shipping, which is a pretty good deal. So I kind of bring that up. So let me just run through the questions here. If you got any other questions, just pop them in there. Okay, how do you keep the food from sliding or falling around and tipping in the solar ovens? Give me a second, I'll show you. It's pretty easy. If anybody's ever been on a sailboat and seen an oven on a sailboat, which you may not have, I've only seen one or two of them. They use what's called a gimbal. So basically, it's really hard to see in here, but there's a metal tray in here. And that's on a little shelf, a metal shelf. And on each side of the metal shelf, there's a steel, like a metal bar that comes up, like kind of up to here on both sides. The top of the metal bar has a hole in it. So you put a screw through on both sides and keep it loose. So this thing swings. And since it's below the pivot point, it's always going to stay horizontal. It doesn't matter how much you tilt the oven, it's still going to stay horizontal. So that's called a gimbal shelf. That's how we keep the food from flying all over the place. Alex said 5 by 5. I'm not sure what that meant.
Probably how he was hearing you. That's a term for that. 5 by 5.
Oh, is that? I'm assuming that's good.
That's a good.
Okay. Have you ever considered about building your own power wall? I have watched the YouTube videos. It's kind of cool because the original power walls are those 18650 batteries that apparently those are the batteries they use in a lot of laptop batteries. So I know one of our members, Nazar, was actually looking into that because he had a line on somebody where he could buy like a pallet of old laptop batteries that weren't good anymore. Well, when a laptop battery goes, there's a number of those 18650 cells in them. So usually what happens is one of those cells dies, so the whole thing is shot, and nobody's going to take one apart to test them. So there's people on the internet that have figured out how to test them individually, and you could make your own power wall just by taking those things apart. You get the exact same batteries as the original Tesla power walls did, and you can make your own. I haven't done that, and the main reasons is I have a generator. It's not a big generator. It's one that'll keep the fridge and freezer running, and that's pretty much about it. However, it's fine for me when the power goes out. And the story I tell people is I have a little log. It's basically just a piece of paper taped to my generator, and I write on there when I've used it. When we had, I don't know if everybody remembers Hurricane. I bought it after Charlie, Francis, and Jean. So at some point after that, I had to change the breaker box out of my house that I told you about before I did the solar. So I had to take the power down for like a day to do that. So I ran the fridge and freezer on the generator. So I logged that on my little log, right? The next time that my power went out that I needed the generator was for a short time during Hurricane Irma. And I'm forgetting the exact years, but that was like that might have been 5 years later, right? So if back when I used it to change my breaker box, if I would have bought batteries for my solar system then, they never would have been turned on once. And I would be replacing them now if they were lead acid batteries because they only last 5 years. Now maybe my neighborhood is very resilient compared to other people's, especially if it's in a different part of the country. But that's my reasoning behind not spending the money on batteries.
So I'll ask you one, Harry.
Sure.
At night when there's no sun, how does your house get power?
The same way your house gets power, exact same way.
Power so you start pulling from the grid.
Exactly. It's just during the day I make the meter spin backwards more than it goes forward at night. And that's one of the reasons I really don't have a gripe with the power company only giving me like 3 or 2.7 cents a kilowatt hour when they buy my power at the end of the year, because I'm still using all their stuff, especially all night. So do those credits with Duke ever expire? That's a good question. And the answer that I initially got was different than reality. And there's kind of a funny story that I tell people along there that I think my wife's actually in earshot, so she'll get a kick out of it. But so when I first started planning all this, I was under the impression, and it may have been fact, that when I got the credit from Duke, they would literally send me a check. And I think at one point that was the deal. However, when I finally finished the installation and everything and did the research at that point, which was many, many years later, the deal was that they didn't send you a check, they credited your account. And that credit that they put on your account would expire after a year. When we were, before I even started putting up solar, I was obviously very frugal, and we were into saving money and saving energy and everything. So we still have it. We have a clothesline in our backyard. So I would tell my wife, yeah, we need to hang the clothes out because we're saving money, right? Obviously we're saving money. We're not using electricity on the dryer to dry the clothes. So at the time that I thought, when I started putting the solar stuff on, that we would get a check. And then it got to the point where I was generating more electricity than I was using. So now I'm thinking, not only are we saving money, I would tell her, we're actually making money by hanging the clothes out. Because every kilowatt hour that we save that we don't use, we're going to get 13 cents for it, right? So it's like, this is awesome. So then the first year goes around, and then I'm told that the credit expires after a year. Well, the first year credit I got was $160. So then I was like, well, wait a minute here. They just gave me $160 and it expires after a year. The only amount that I'm going to use of it is the $10 a month. So I'm only going to use $120 of this $160, and then I'm going to get that $40 is going to go away. So now I'm telling my wife, don't hang the clothes out. We're wasting money because I'm wasting $40 that it's going to expire. However, when the next bill came around, that was that actual one of those bills that I showed you that February. The credits from the previous year do not expire; they just keep rolling over. So that information, which I'm pretty sure I got from Duke, isn't quite right. However, there's only so many people in Florida that are doing what I am doing and generating more than they use. So. About adding your lithium batteries to your camper, the only thing to research that I honestly do not know is how we charge these batteries for the power racers, those lithium ion batteries. I'm not sure how you do. Obviously somebody does it, you just have to figure out who. I'm not sure how you would do all that technical stuff to make sure the lithium battery gets charged, the per cell type thing. Because I don't think you can just clamp a regular battery charger onto it and start charging it that way. But I have seen the inverters that are designed, or I'm sorry, charge controllers that are designed for campers that specifically state that they support lithium-ion batteries. So yeah, so those probably have some type of battery management system in them, I would imagine, like Brian said. I haven't done a whole lot of the charge controller stuff, but it's pretty simple for normal lead acid or sealed batteries. Anybody else have any other questions? If not, then if anyone is interested in touring the MakerFX Makerspace, we would be happy to give you a tour at some point. It's usually one-on-one tours now under normal non-COVID life. We have an open make every Friday evening. A whole bunch of us get together and kind of show the space and show what we're working on, et cetera, et cetera. That's actually been moved to virtual now, so feel free to join that if you want as well. It's usually every Friday at 7:30. So, like I said, if anybody's interested in touring the space, just let us know. Other than that, thanks everybody and have a great night.
Thanks for presenting, Harry. And again, as Harry said, if you guys are interested in a tour, we can do those one-on-one. If not, the open makes are 5:30 Friday, and there's links usually in our Slack and on our Facebook. So thank you, everybody, for joining us, and thank you, Harry, for presenting and sharing your information. I know I learned a lot, and I know everybody else, I'm fairly confident, did as well. So if you have any other questions, guys, that you didn't think of tonight, you can always email them to info@MakerFX, and we'll make sure that those get over to Harry. So thanks, everybody, for your participation, and thank you, Harry, for presenting.
All right, thanks. Have a good night.